Hi everyone, I'm Fabio Nonato, a Principal Solutions Architect with AWS, and welcome to our talk today on accelerating deep learning model building using AWS HPC services. Today's session, I want to walk through three main topics. First, we'll talk about the workload we're targeting, which is building deep learning models for natural language processing. Then we'll follow that up with the infrastructure implications of these types of tasks. And then we'll wrap it up with a quick look through our recently published distributed ML workshop that's available through our hpcworkshops.com website. So when we start talking about deep learning and AI for natural language processing, some examples that normally come to mind are us talking to our robot assistants. Alexa is a voice assistant that uses machine learning and AI to generate voice out of text. So in this text-to-speech applications, there are two main tasks supported by machine learning. First, the context generation using a neural network, followed by speech generation. But that's not all that natural language processing applies to. Organizations across different industries generate and consume a vast amount of unstructured text data. For example, in financial services or legal services, there is the need to extract information from documents and sometimes correlate entities and information across documents. This is something that also applies to manuals or service reports on industrial systems. This list I show on the screen is far from being a complete, exhaustive list of all use cases, but start shedding the light on the initial steps that we take to convert large amounts of unstructured information into structured data that can be leveraged to bring value to the users through analytics. So, what are we fundamentally doing when we're talking about natural language processing? As scientists, we tend to prefer running algorithms over well-structured mathematical representations of data. So processing a vector representation in a real space takes us much further than just running analytics over a bag of words. So when we are actually speaking or texting or robot assistants, we need a system that can take the natural language sentences as inputs, embed them into a vector representation that preserves the context and semantics of our text, so we can then run the analytics over those embedded vectors. So a simple example is those two sentences on the screen. We went to the riverbank, and I need to go to the bank to make a deposit. Despite both sentences having the word bank, the semantics are completely different. The first one, it's a riverbank. And the second one, it's a financial institution. And we only know that because there is context in the sentence as underlined that gives us a tip for what the actual word means. So, what magical device can we use to actually learn the context and semantics of words within sentences? That is the job of natural language understanding type models such as BERT, or the full name, Bidirectional Encoder Representations from Transformers. And there is a lot to unravel just on the model name itself. The first thing we take out of it is that it's based on the Transformers architecture, and it leveraged the encoder part of that architecture to generate the embeddings. The original BERT model has different sizes. It can be a BERT base, it can be a BERT-Large, and that actually indicates the number of those encoder layers that we stack to get us to the embedded layer or the hidden layer, which computes those embedding vectors. The size of that embedding layer is also important, and those two characteristics actually control the number of parameters that this model has, and we need to train so it can actually embed sentences and understand the context of the word bank, for instance, in those two sentences. Training this embedding section of BERT is what makes it an interesting computational challenge. which we can solve with AWS HPC services. The training process of BERT has two stages. The first one is an unsupervised training of the main models over a very large data set called pre-training step. This step actually impacts a lot on the compute and memory requirements of our infrastructure. The following step is where we actually fine-tune the model to specific NLP tasks like we saw on the list. But today we're going to be taking a closer look at the pre-training step, where we can either use a masked language model strategy to train the model to find the context and predict masked words, or next sentence prediction. So let's take a look at each of those training challenges. First, compute. The BERT-based model that we're going to be looking in today has actually 12 encoding layers with a 768 dimensional hidden layer for a total of 110 million parameters. During training, we will need to compute floating point matrix multiplication over all those parameters, then calculate the gradients based on a defined loss function, and propagate those gradients back to update the parameters of the network. That's what's called backpropagation for deep learning model training. And we do that for each sentence over and over again. Hence, we will require some hardware acceleration to complete training. Just to put it into context, if we train BERT on a single multi-GPU machine, it can take up to 7.5 days on one of the largest GPU instance you get on AWS, the PSdn 24X-Large. Now, if we distribute this training across 256 instances, the time gets down to 62 minutes, which is a much more reasonable time frame for a model experimentation step on a normal machine learning workflow. This truly shows how distributed training requires HPC scale. If we compare this BERT model to the largest natural language processing models you see today, such as GPT, there is 10 times as many parameters in GPT-2 as in BERT, and the current iteration of GPT-3 has 110 times that. So NLP actually grows very large very quickly. For the next challenge, we looked at storage and memory. BERT gets pre-trained on a lot of Wikipedia text, actually 2,500 million tokens, plus 11,000 books. This amount of data does not fit in a single GPU memory. And this means that the problem is memory bound. And we have to create batches of this data that will be sharded across each GPU. And the rule of thumb is, the larger the size of those batches, the faster we can train the model. So this data loading strategy is an early on decision during the model building phase that has a direct impact on the infrastructure for model training. Training is indeed a very read-intensive job that usually requires a few different data paths. To set up ML environments, we usually use shared file systems such AWS Elastic File System or a multi-attached AWS Elastic Block Storage system. So, and for training data, we can use Amazon FSx for Lustre to provide high-performance throughput file system with POSIX access to the data, which fits a large number of ML data loaders frameworks. Finally, networking. Once we have multiple GPU instances, communication between GPU is important for fast training times. Within the PSdn 24X-Large, GPU communication happen at 300 gigabytes per second using the NVIDIA NVLink from the chassis. Across instances, we can leverage Amazon Elastic Fabric Adapter for ultra-low latency communication at 100 gigabits per second. The Elastic Fabric Adapter integrates well with the major ML communication libraries such as NVIDIA and CCL, allowing us great flexibility when designing our data and model parallelism, as well as our gradient synchronization strategy. So, and to achieve the combined total of all these technologies, we can leverage Amazon Parallel Cluster, which is an open source cluster management tool that we can use a single text-based configuration file to set up our compute infrastructure in a secure and scalable way. Parallel Cluster also seamlessly integrates with a variety of schedulers, and that allows us to automate the infrastructure provisioning with minimal manual intervention. So let's take a look on how to set up a cluster to run distributed machine learning with AWS Parallel Cluster.
Okay, so let's start with the hpcworkshops.com website. Here you have a collection of self-paced tutorials built by HPC and ML specialists from AWS on how to run HPC workloads on the cloud. This collection helps you get familiar with the concepts and best practices around AWS services supporting large distributed compute workloads. The tutorial levels span from getting started with HPC on the cloud all the way to running large-scale batch jobs and distributed machine learning, which is the section we will explore today. First, we set up an Amazon Simple Storage Service bucket with the data required for training BERT. We will use the subset of the Wikipedia text data just as an example. The tutorial walks you through how to download it from the internet and copy it into the bucket. This way, we can make sure the data is available to the worker nodes in our cluster using Amazon FSx for Lustre. The workshop also shows how to use the cluster to pre-process the data prior to training. We will not cover this section today, but I encourage you to take a look at it. We also create the configuration file for Parallel Cluster with all the features we discussed previously: a shared Amazon Elastic Block Storage, Amazon FSx for Lustre, and Amazon Elastic Fabric Adapter. We also are going to use the P3DN 24X-Large instance as our worker nodes. So let's get started. First, in our own local environment, we are simply downloading the Wikitext 103 dataset from an existing public Amazon S3 bucket. Then we copy the whole downloaded folder into our own bucket that we just created. This way, we'll make sure all the files are available for pre-processing later on. After that, we'll create what we call a post-install script. In this script, we will configure the environment we need to run a deep learning model training job. First, we will install the NCCL NVIDIA Communications Library. That is the library we're using for our gradient synchronization. We are also installing the AWS plugin that allows us to use NCCL with Amazon Elastic Fabric Adapter. After that, we are going to move into a shared directory that we'll configure later on to be backed by a multi-attached Amazon Elastic Block Storage. In this directory, we install a machine learning package manager called Miniconda. We also install FairSec, which is an open source framework for training natural language understanding models created by Facebook. Once the script is created on our local machine, we're not going to run it. We're copying it into the same S3 bucket so that Parallel Cluster can use it when spinning up new worker nodes. Let's take a look at cluster configuration next. But first, we need to create a key pair. Amazon Parallel Cluster will use this key pair to allow us access into the head node. So make sure to set the proper permissions on the key, as well as keeping it safe. Now for the cluster configuration file. We'll spin up the P3DN instances. Those have 8 GPUs per instance, and are EFA enabled. These are pretty large machines, so we're not going to be using too many of them. We are setting the cluster type to spot. This type of instances are available at a deep discount. However, they might be subjected to interruptions. In a machine learning workload where you can save the model as you train it, you might be able to restart an interrupted job. However, to guarantee elasticity for a large-scale production machine learning workload, try leveraging other types of instances, such as on-demand. We should also refer back to our post-install script in the same bucket as our data is. So we'll set up permissions for Parallel Cluster to access the script in the bucket. This configuration file has to be built on a local machine where Parallel Cluster is installed. Check out the installation process in the Parallel Cluster user guide. Here is an example of a configuration file. We will call it myml-cluster. In this file, there will be a cluster default section where we reference back to all the points we discussed before, including the type of instances. We'll be using P3DN 24 X-larges for our compute instance type, and the C5 2X-large for our master type, because we don't need GPUs on our head instance. The cluster type is spot, and here are the permissions that we're going to set on our bucket, as well as the path for our post-install script. We'll have two sections for data, one for the EBS volume backing the share directory, as well as the FSX for Lustre section, where we define the path for our worker and head nodes, as well as the capacity, and the path for the bucket that contains our data. FSX for Lustre will load the data at its initialization from this path. We'll create the cluster by running pcluster create myml-cluster and pointing to the configuration file we just created. Today, we're not going to be taking a look at the pre-processing step. I already set up a cluster with all the data in already pre-processed, so we can directly run distributed data parallel training of BERT using PyTorch and FairSec. Let's go there. This section shows in a step-by-step way how to build the scripts needed to run the distributed data parallel training of BERT. But instead of looking through here, let's get our hands dirty and check out the code. I'll open my AWS Management Console and navigate to Cloud9, a remote development environment sitting on top of a EC2 instance that I can use to deploy the cluster using Parallel Cluster. It will take just a second to open, and we'll have our environment there. You can already see my ml-cluster.ini files here. So if I run pcluster list, we see my ML cluster on the top of the list. This is the cluster that I deployed before the workshop started and ran the pre-processing of the data on it so we can run the training. To log into the cluster, I'm going to use pcluster SSH, the name of the cluster, which is my ML cluster, and pass on the path for the key we created before. Now we're in the head node of the cluster, ready to start looking through the files. On the home folder, we see the NCCL library and the AWS OFI NCCL plugin installed. We should also check that EBS volume that is mounted on a share folder to look for FairSec or ML library to train BERT. And if we move into the Lustre folder, cd/Lustre, we can check out the data that has already been processed and the pre-processing script and the two other scripts we're going to need for training, job.slurm and train.sh. In job.slurm, we'll see the configurations for our distributed world where we're actually going to run the training job. So we call out 2 nodes with 8 GPUs each. And we are actually also setting up exclusive single tasks per node. Now, this is an interesting configuration because we're running 2 tasks, and the parallelization across GPUs within a single machine is going to be done by PyTorch for a total of 16 training tasks. Slurm is actually only scheduling the 2 tasks on a queue that now is empty. So if we go and look at our training script, we set it with a few different sections. First, the directories we're going to use both to load the training data and save the model. Then the environment variables that configures the distributed training, mainly coming from our scheduler Slurm. Followed by the environment variables setting up NCCL and EFA. After that, the code is basically the same code any machine learning practitioner would have to write to train. In this case, we're using PyTorch distributed launch to launch the 8 jobs per machine. So let's use the spatch command to run our job.slurm script. Here, the job ID is 25, and we can check now on our queue if it got scheduled. We already see 2 resources being consumed, the 2 IPs listed on the queue. Those IPs are already there because I've already pre-provisioned the machines before running this job. If this was the first time we were running, Slurm would trigger the auto-scaling group created by Parallel Cluster to provision 2 new machines for me. And here you also see the out25 job output log. Let's cat it and see what's in it. Besides a lot of verbosity from our training frameworks, we can check now the distributed environment. Here you see all 16 workers, 1 for each GPU available. Okay, so all the workers are already loaded. We might as well check if we're getting consumption of memory and processing on the GPUs. For that, I'm going to grab one of those IPs and SSH into the machine to check the NVIDIA SMI command and see the percentages used. So let's log in and run NVIDIA SMI. There you go. We have 8 processes, 1 for each of the Python threads, consuming close to 100% of each and every GPU. That's quite neat. Okay, we can go back to our head node now and check for what's happening on that output log. Let's follow it. All right, now we are already logging out some of the epochs during training. And right in the middle there, we can see WPS, or words per second, which is getting us close to 65 or 66,000 words per second. That's quite a good performance, very close to what is shown on the workshop itself. If we disable the Elastic Fabric adapter on these machines and get TCP communication at slower speeds, our benchmarks have shown that this number, 66,000, goes down to around 58 to 59 at peak, and we take a hit in performance. And now, to remove the magic, I'm just going to skip ahead to the end of the training, just so you can check out how does it look like. Right, we kept a steady pace of around 60 to 66,000 words per second, and we ran a validation step at the end of our first epoch. That's where our training ends for this workshop. This is definitely not the best model ever. The evaluation shows that we can go way further, and we don't have enough data to do so. But hopefully this gave you a very good understanding of the whole setup of infrastructure, setting up of scripts, and how to run distributed data parallel training using parallel cluster.
Okay, so now that we've seen how to run distributed machine learning using parallel cluster, how large can large-scale machine learning be? So if we take a look at this chart of the speed-up factor from a 4-node test, which is double the amount of nodes we use today, we can see that we can have up to 14 times faster training time if we go to 128 nodes as compared to the 62 minutes we'd see on 256 nodes. So by using parallel cluster and all the other services we saw today, we can drastically reduce the model training time by distributing the workloads across hundreds or even thousands of GPUs. I want to leave you with a few links. The first one for our distributed machine learning workshop that we saw today, and the second one to the actual open source version of parallel cluster. The third link is a link for the machine learning framework we use today to run training for a BERT-based model. Thank you very much.